get started. All right, so so we sent out emails to everyone who didn't fill out the course evals last lecture. If you got an email about an hour ago, fill out your course evals. It only goes out to students who did not fill out their evals. So we got an email sent to everyone left. But we are doing pretty good. We did hit the 70% incentive, averaging out across the courses. And the email didn't give us an immediate boost like I'd hoped. The remaining students are probably pretty stubborn. I was surprised to find out, but there are some students who will deliberately not fill out the course evals once they hear there's an incentive. It's ridiculous how some people act. But if you're one of those people and you don't like what I said, fill out your course evals and tell me about it. But we did hit the 70%. So the application task 2 deadline has been extended to next week. We did hit the end of the extended deadline for application task 1. So if you still didn't finish application task 1, you got to hope that we hit 80%. I think we'll get there. I said this last lecture too. I think we'll get to 80%. But it'll also be a question of when we get there. If we get there, but it's like right before when that deadline would be extended, or right after. I forget how long these go. Ends 5/14. So there's a possibility we'll hit it after this deadline, which wouldn't be helpful. But I think we will get there, but we'll see. There are always surprises. Hopefully you all have application task 1 done anyway, though. Those of you who are still showing up and coming to lectures. So that's where we're at with that. Monday is going to be the TA lecture. I mentioned this last time, but just a reminder, I might not be here at all on Monday. I might come in and just introduce the TAs. But that's the open and honest lecture where you and the TAs can talk about, that's your time to talk about whatever you want to talk about, whatever you want to ask the TAs. And I know Leo's not going to hold back. He's going to tell you what he thinks about everything. And he'll give you some really great practical advice that will be very useful for whatever. Presumably you'll ask about CS stuff and professors and classes and stuff, but I'm sure he would be happy to answer any question outside of that as well. So I might see you there. I have to come in for 312 anyway that day, so I might end up coming in, hanging out, and just introducing them at the beginning of each lecture. Why do attendance on autograders have to be graded manually if it's just an ABCDE answer? Good question. Nicholas, you want to answer that one? Yeah, good question. So we can have the autograder added to there, but we do have a bottleneck, which is actually the front end of AutoLab, where once like 100 or so students are all submitting their answer at the same time, it does get a little bogged down, and then there are students who can't get in their lecture question. So it is still auto-graded, kind of, but I upload the grader after and then hit the regrade all button so that it goes through and regrades them all, which is progress because we used to not be able to do that. I used to download all the submissions and then run a script and then upload all the grades. So we are getting better with that one. But ideally, you'll submit, it'll be auto-graded, but then you won't see your grade until after the question ends. Or else one person will submit and then say, "Oh shoot, it wasn't A. Don't submit A," and then things like that'll happen. Am I ready for the fight on Friday? I'm always ready. I'm ready. I can't believe y'all voted for that. And we're. This is what I did the wrong one. I'm dumb. This is what 312 voted for. We're gonna have fun in 312. I'm in my settings right now, but but y'all want to see me and Paul fight, so I guess that's fun too. Got to wait for my laptop to register again. Okay. So what we want to do today is... Oh, yeah, thanks for mentioning that, so I don't forget to say this. There's no lecture questions next week. So today's going to be the last lecture question of the semester. So next week will not count for lecture questions. All right, so what we want to do today is sorting. Yay, merge sort specifically. But I'm going to start by setting up some test cases for our sorting algorithm. So I'm going to do some setup here, test sorting. And get rid of all of this graph stuff. Get rid of this. Get rid of all of this. And test. What I'm going to start is a test that's going to test insertion sort. So I'm going to create an instance. I'm going to use our insertion sort code from way back in week 6, forever ago. So insertion sort of, and we're going to sort some doubles, just to keep things a little simple. I'm going to sort doubles. Sorter seems fine. New insertion sort of, I don't have to put anything there. And then new, I had to write this new class. Actually, I'll write it right here instead of copying it over. I don't want to cheese it. Double, so last time we did int increasing, and then I tried to use that to sort doubles in the previous lecture, and it doesn't work like that. So let's write a double increasing so we can sort doubles just in standard increasing order. So double increasing is going to implement extends, because we're using the week 6 code before we were using interfaces at all, extends comparator of t. That's not how that works. Comparator of double. And then we don't get our override or errors or anything because comparator is a concrete class, not an interface. So I have to remember exactly what this is. Boolean compare. And then if I get it wrong, I'll get an error. Double D2. Return D1 less than D2. Okay. And I don't have any errors, so it looks like I got everything right. But it say I spelled compare wrong. I'm going to get an error here because my override annotation is going to have me covered on that one. So double increasing. Make sure I didn't get an import, so I don't have the wrong one here. Just the insertion sort from week 6. That's all we want to import. And then we're going to create a new list. I want to create a random list. And we're going to see something that we haven't seen before in our tests. I'm going to embrace some randomness here. Now, generally, I don't like randomness in my tests, but we're going to embrace it today just for the sake of our examples. Also get kind of complicated to build them out. So we're going to use some... Oh, I never updated that. Yeah, the schedule is wrong on that. There's not 3 lecture questions next week. I have to update that chart. If I have that open, I'll do it right now. I might do it right now anyway. Of course, it's going to be on small font. So what I want is a method that's going to return, and I'm going to use interfaces here, a list of... Did I get away with that last time? No. Yeah, this does have to return an array list. I was going to say that shouldn't work, but I thought I did it last time. We're going to return an array list of double. Because we're interacting with our week 6 code before we knew about interfaces, all that is hard-coded to array list. So we do have to use an array list here. and not the list, the interface. Yeah, and I'm going to be small text. Let's see if I can just do this quick. I'm just going to delete these ranges because I don't want to compute them right now. I usually hold myself to what's on the syllabus, so we could have lecture questions next week if that's what we want. I don't think anybody does. Private array list of double random list, and we're going to generate a random list of size n. So I want a random list with n random doubles in it. So I'm going to create an array list. Array list, I have to use array list here, of double. Call it numbers equals new array list. And I'm actually going to use one of the constructors of an array list that we have not seen before. I know how big this array list is going to be, so instead of creating a small array list and having Java constantly double the size of the underlying array and going through all that, I'm going to use the constructor that gives a default size to this array list. I know I'm going to have n values, so I'm giving Java a heads up. Giving the array list class a heads up like, hey, that underlying array, make it of size n, because that's how many things I'm going to put in this array list. And then I won't have to suffer through that doubling size. And then for I less than n, numbers.add math.random, which math.random is going to give me a random double between 0 and 1. Just super handy, but usually not exactly what we want. In most languages, you're going to have some random function that works the same way. It's going to give you a value from 0 to 1. So it's going to have some 0 point and then some decimal portion that's randomly generated. It's not exactly what I want here. So what I'm going to do is shift and scale this range. So if this is from 0 to negative 1, and I subtract 0.5 from it, now I have a random value from negative 0.5 to positive 0.5, and then I'll multiply this, just manipulating this to get whatever range I want. I'll multiply it by 200. So this is going to give me a random value in the range negative 100 to positive 100. So I can manipulate that to give me the values that I want, and then return numbers. So I got my sorter. I can get my random list. Numbers equals random list of n. And I'm actually going to put n, actually I'm not going to name it n, private final int number. So if I just name this n, I'm going to have a naming conflict with this variable here. And things are going to get, my scoping rules kick in. I have to make sure that I'm accessing the right variable at the right time. So I'm going to give this a different name just to make sure I don't make that mistake. Int number of elements equals, and we'll generate a list of size 100. This dot number of elements. Hell, we can even make this static if we want to get fancy with it. When you have a static constant like this, you typically put it in all caps by convention. So we got our numbers. We're going to say sorter.sort numbers. This is going to return a new array list. I'm actually going to switch to the interface. So once we're outside of this sort method that's hard-coded to array lists at this point, now I'm going to start using the interface, so I can start using just the list interface. Sorted numbers. I'm going to do a few checks on this to make sure that sorted numbers has everything that I want it to be. I want to assert that this is actually sorted. So the first thing I want to do whenever you're doing any asserts on a data structure, the very first thing you should check is, do I have the right number of elements? Number of elements, sorted numbers dot size. Because we're going to check if these values are in sorted order, but if this method just returns the empty list every single time, it's going to be in sorted order, and but I'm not actually checking. And for full thoroughness, we should check to make sure it has all the values in the original list in the output list as well, to make sure it doesn't just have the same number of elements, but it has the same exact elements. So a few extra things that we would test if we had more time to flesh out the whole test suite. And notice that I'm using number of elements here to check the size of the sorted list and not numbers.size. The danger of doing numbers.size right here is that I gave a reference to numbers to my sorting algorithm. So if my sorting algorithm went to the heap and messed with that array, it might not be, it's not my ground truth anymore. My ground truth is number of elements. I have this value here. I didn't give it to anything else. Nothing else had a chance to change that value. In fact, it's final. It can't change. So I know that this is my ground truth. This will be exactly what I expect. But numbers.size, numbers might have gotten blown up by my algorithm if it's really bad and it's making changes to that array list. I don't want to do that. And then let's actually check if this is sorted. I'm going to do another helper method for this. Void check if sorted. List of, we're going to hard code things to doubles. Numbers. And we're going to do that trick that we've seen quite a few times by now. It's getting to be old hat now. I strictly less than numbers dot size minus 1. So we're doing less than and minus 1. So we're going to stop 1 before the last index, I++. And then I'm going to check. I'm going to assert true. And I'm sorting in increasing order here. So numbers dot get I plus 1 is greater than or equal to numbers dot get I. So I want to make sure I'm non-decreasing. The numbers can be equal, but we're working with doubles, so that's unlikely. It would have to be equal even after the possible truncation errors and everything. So I'm going to assert that each value is greater than or equal to the value that came before it. So that's going to check if my list is sorted. Check if sorted numbers. So we have a test case that's going to test our insertion sort method that we saw before. And for good measure, I'm going to print numbers, just so we can actually see that something happened, because seeing either a red X or a green check mark, there might be something really wrong with our test itself, and we'll still pass. So just to make sure, get more confidence that our test is doing what it's supposed to be doing and our code is doing what it's supposed to be doing, we'll print those out. So we got our green check mark, our insertion sort's working good, and we can see the random list of numbers that we generated are random values from -100 to +100. And when we print it out sorted, we're getting the lowest values first, which are the highest negative values, and then it's increasing, or at least non-decreasing, throughout the whole array list. It's just some spot checks. I'm not going to look at every single value here, but I'm gaining confidence that my code is actually right. It looks like we have the same number of elements. The numbers really appear to be increasing, and I went to check if sorted, so I'm feeling pretty good that My code's doing what it's supposed to be doing. So now let's get into the good stuff. I'm going to duplicate this whole thing and write a test for merge sort. I want to merge sort. I want to merge sort. Everything else should be fine. And I want to create a merge sort class, which is going to follow the same structure as my insertion sort, bless you, but it's going to, of course, do merge sort instead of insertion sort. So merge sort takes a type parameter, or a generic because we're in Java. We're going to have an instance variable, which is a comparator of t. Week 6 comparator, make sure I get the right one. Comparator. I'm going to have IntelliJ write my constructor for me. And then public, I'm going to code to the interface because we know what interfaces are now. Public list of t, sort list of t. Input, sounds good. Is it going to let me import now? Okay. And then return null just to get a stubbed out method that will compile, even though it doesn't do anything. Signed, but never accessed. I never used my comparator. And let's go to our sorting just to make sure all the errors went away. And we can run this, but we'll get a null pointer exception because we're returning, sort returns null, and we're immediately calling its size method. Can't call a method on null, so I'm going to get null pointer exceptions. Can't invoke size because sorted numbers is null, exactly what we expect. Okay, so let's get rid of that and actually implement merge sort. So, merge sort. You've seen this very briefly in 1.15, so let's talk about it again. So merge sort is a method that's going to take a list and return its element sort. It's going to sort. But it's going to do that using recursion. So we know what recursion is now. You didn't know what recursion was when you saw this in 1.15. So we're actually ready to talk about this now. We're going to use recursion to sort the list. And what this is going to do is first, if the input is obviously sorted, we're just going to return it. So what do I mean by obviously sorted? How would I know if a list is obviously sorted? Like, what list could I give you where you're just like, it's obviously sorted, like it's sorted? How about if its size is less than or equal to 1? I'd say that's obviously sorted. So if its size is less than or equal to 1, I give you a list with one element in it, I cannot convince you that that list is not sorted. It's only got one element. It's sorted. It's clearly sorted. I give you an empty list and try to convince you it's not sorted. You shouldn't believe me. You shouldn't believe anything I say. That thing's sorted. So if the list is either size 0 or 1, the thing's sorted. Else, we have some work to do. Else, if the list is not sorted, what merge sort is going to do is magic, the magic of recursion. So what it's going to do is split the list in half and recursively call itself and just say, well, I couldn't sort this list. Maybe I can sort it if it's smaller. So we're going to chop this list in half. For that, I'm going to get the index of the midpoint of this value, input.size, over 2. And for this, I'm going to embrace integer division. I want this to be integer division. I'm getting the index of the midpoint of the list. And then chopping it in half. The left is going to be the input dot sublist 0 to mid index. When I'm chopping this list up, I want to make sure that mid index is not a double. It has to be an integer value. So if size is odd, I don't want to try to get the value at index 15.5 because I'm going to get errors, all kinds of errors. I'm going to get sublist requires int got double. We're going to get errors like that. We don't want that. We need this to be a whole number. So we're going to use integer division by 2. So any odd numbers are going to be rounded down to the next whole number. So I'm going to get the left side of the list. I'm going to get the right side of the list. And sublist does what the name implies. We're going to chop this list in half by index. So give me all the values from 0 to mid-index exclusive of the mid-index. It's always inclusive of the first index, but exclusive of the last index. So inclusive of mid-index, and then exclusive of input.size. So there is no value at the index input.size, but it's exclusive of the endpoint. This is where it's very easy to make a mistake where you're losing some elements. You're either losing the last element or the element at the mid-index. So that's where it's nice to have our check to make sure that the returned list is the right size. Making sure it is the right size, that's making sure that we didn't make some mistake in there where we're losing elements along the way. So we want to make sure we didn't lose anything. Hopefully I got this set up right to not lose any elements. And then, now that we have this list split in half into this left and right halves, I'm going to sort them. And how am I going to sort them, though? How am I going to sort each half? Well, I mean, we have a sorting method. It's the method we're writing. The method we're writing is going to sort lists. And we have the need to sort lists, so why not just recursively call the method that we're currently writing, that we haven't even finished yet? That feels counterintuitive. You're human, because that does sound super counterintuitive. But we're just going to have the method itself call itself to do the job that it's supposed to be doing. Instead of actually sorting things, we're just going to defer to the method itself to do the thing. I mean, why would we do anything else, right? And then we're going to assume, as we do with recursion, we're going to assume that these method calls do the right thing. We're going to assume that this actually did give me left and right, all the elements in left and right, but in sorted order. Through the magic of recursion. We always just make that assumption when we're writing a recursive method. You assume the recursive calls return the right values. We're going to assume that those return the right values. And what we're left with, our last task that we have to do, is merge these two sorted lists. And I'm going to do this in a helper method, private list of t merge, list of t left, list of t right, and stub it out just so we don't get errors while we finish up here. So we're going to write a method that merges those two lists into one single sorted list. And that's what we're going to return. And that's it for the sort method. This is it. I'm not going to change any code here unless I made a mistake, unless I have to go back and do some debugging. I'm done with that sort method. My only task left is to implement merge. And merge, if you feel like we haven't done anything yet, you'd be right. And merge is going to do the work for us. The merge part of merge sort is critically important. So we're going to merge. And merging seems like it has all the work to do. So if we could merge, if you can give me two lists, and I can merge them and return one sorted list containing all the elements from both lists, well, it sounds like we haven't made any progress, and our task is just sorting, which is the same task that we started with. But there's one key difference here that makes this possible, or makes it possible to get efficiency out of this, or else why would we do any of this, is that left and right are already sorted. So we're going to leverage that assumption that left and right are both sorted already which we're assuming because we're just assuming sort did what it was supposed to do, which is the method we're writing. And if left and right are both sorted, then how do we merge these? And that we can do faster. If left and right aren't sorted, it is just the sorting problem, and we have to start from scratch. But since left and right are both already sorted, we're going to take advantage of that to write our method. And the way our merge method is going to work is we're going to start at the first element of each list and ask ourselves, ask our comparator, which one of these two comes first. And whichever one comes first, we're going to copy that to an output array list. And then look at the next element in that list, and then compare the two elements we're looking at. And then whatever one comes first, copy it to the output, and then advance to the next element in that list. And then do that till we hit the end of one of those two lists, and then copy all the values from the other list over to the output. So let's see what that looks like. First, we're going to create our output list as a new array list. And I know what the capacity of this array list is going to be. And at this point in the semester, we are talking about efficiency. It should make sure that's clear. We wouldn't do this at any other point in 116. Left.size, right.size, because this is basically a preface to 250 at this point. So we're going to get the output. We're going to set its initial capacity so we don't have as much resizing inside this array list. Output is what we're going to end up returning. And I want 2 pointers. I'm going to call them index, 2 indices that tell me which value I'm looking at in each list. And then I want to check if left.get of left index, so give me the value that we're looking at with the left index, and right.get right index I'm going to compare those two values. And if the comparator is going to return true, if the first input comes strictly before the second one. So if this is true and I make it right here, that means left goes first. So that means the value in the left list comes before the value in the right list that we're looking at based on these 2 indices. So if the value in the left list comes first, and these 2 lists are already sorted, so I know that the value I'm looking at in the left list comes before anything that comes after it, and it comes before the value we're looking at in the right list. Therefore, it also comes before all of the other values that are after that value in the right list. Well, then this value right here must be the next one that I want to add to my output. So we're going to say output.add that left value, and then we're going to increment left index to look at the next value in the left list. So when this is the first element, when we have indices 0 and 0, we're looking at the first element in each list. These are the smallest elements in both lists. So whichever one of those 2 is smallest is going to be the one that comes first in the output. And that cascades into every other check. If we go advance to the next element, we already have everything that came before left index is already set. It's already in the output, and then we're going to advance to the next one. Else, our comparator returned false. This means right goes first, or a tie. We're just going to choose to break ties to the right. Output.add right.get right index. It's the second time I did that. Right index plus plus. So we're going to copy the value from the right list and then increment the right list index. And then we're going to do this until we reach the end of one of the lists. Right now we just have a conditional, so this is going to get 1 value in the output and then return a list of size 1. So let's get this in a loop. And I want to loop I haven't reached the end of either one of these lists. So So I'm going to carefully write my Boolean expression. I struggled with this in the previous lecture, so hopefully I get it better here. So left index is less than left.size. So once that's false, once left index is equal, increments until it's equal to left.size, this should be false. That means I've hit the left list, the end of the left list, and right index less than right.size, which would mean I hit the end of the right index. So as long as I have not hit the end of the left list and I have not hit the end of the right list. In other words, once I loop until I hit the end of either list, then get out of this loop. Once we're out of that loop, once we hit the end of one of the two lists, that means that we don't have any more comparisons to do. So if one whole list is in the output and we still have values left in the other list, we know that all of those values come after all of the values that are already in the output list, so we can just copy them over. We're just going to copy everything that's left over. So to do that, I'm just going to copy some of this code over. So we haven't reached the end of the left loop, or the left list. I'm going to do the same thing here. I'm going to copy things over from the left. And we haven't hit the end of the right list. I'm going to copy in everything from the right. So since we're out of the first loop, we know we've reached the end of one of the two lists. So one of these two loops isn't going to do anything. Say we hit the end of the left list, but we have stuff left in the right list. This loop isn't going to do anything. The conditional is false as soon as we get there. But then this loop is going to loop through the rest of the right list and get everything copied over to the output. And if we reach the end of the right list up here, then this loop is going to copy the left list, and this loop won't do anything. So one of these two lists is always going to do nothing. But if we have them both there, we're going to make sure that we get the remnants from either list, whatever list we didn't hit the end of, and just return the output. So my claim is that this merge method is going to take two sorted lists and return one full list with all of the values from both of those lists in sorted order. And that method's done. That's what we want that to do. So if we go back to our main method, if we get a list that's trivially sorted, we just return it. Otherwise, we split the list in half and make two recursive calls. This is, if you've heard of it, this is called divide and conquer, by the way. I forgot to mention it by name in the previous lecture. So we're going to divide it into two smaller lists and then make the recursive call to sort those smaller lists. We're just going to assume that those are sorted, that the method did what it's supposed to do, and we're going to merge those two sorted lists into one big list and then return it. So we divided this, conquered them, and then merged into one bigger list, which should still seem like magic. This is tricky stuff. It takes a while to understand, or at least it took me a while to understand how the hell this works, because it seems like magic. How this is actually working, say I get an input of size 100. I get a list with 100 elements, and the algorithm is going to split that into two lists of size 50 and make two recursive calls. Each of those recursive calls are going to get a list of size 50, break it into two lists of size 25, and make recursive calls. So now I got 4 recursive calls of size 25, and then each of one of those is going to make recursive calls of 12 and 13. The right side will get the extra element, the way we're using integer division, and then keep breaking those down and just keep making more and more recursive calls until we hit the base case. Eventually, we're going to have two lists of size 1 that both hit the base case, and then we can finally make it past these recursive calls. We finally get a stack frame that's going to make it to merge, and the first time merge is actually called, remember we have that assumption that merge is going to get sorted lists. The first time merge is actually called, both lists will be of size 1. It'll be when the base case said, yo, these are sorted, it's just one element. So merge gets two lists of size 1 and returns a list of size 2. And then that is the return value of one of these recursive calls. The next one will do the same thing, assuming we have an input of size 4 and break it into 2 and 2 and make recursive calls. The next merge sort is going to merge two lists of size 2, or two lists of size 1. Merge is going to return a list of size 2 in sorted order. And then the next stack frame is going to get those two return values and get two lists of size 2 that are in sorted order. It's going to take those two lists of size 2, give them to merge. Merge is going to merge those two lists of size 2 into one sorted list of size 4. So there's going to be a recursive call, which will get two sorted lists of size 4. Merge will merge those into a sorted list of size 8, and so on, so on. So merge is doing the sorting as we're going up the recursion. And our assumption that we just say, well, we assume this is true. Well, it's true because merge is doing its job, and it started with the base case. So merge starts with the base case and keeps merging lists until we get one overall list with all 100 values all sorted. Who believes me that it actually works? You believe me? You believe me too? Oh, shit, yeah. The last lecture was like, they all shook their heads like, there's no way. So let's test this thing. We'll run our same test. Now there's pressure. I hope it actually works. Ooh, all right. So it did work. We can verify manually too. You know, the test worked, but we can verify manually. Looks like it's doing its job. Let's go to the end, make sure it's the same size. And your faith was well placed. I feel good. All right. So let's do one more thing. Well, we'll do a few more things until we run out of time. I want to run both my tests. Okay, so merge sort and insertion sort, both sorted. They're both green barring. We have two functional sorting methods. But I got one big problem with these results here. Big problem. The whole point of merge sort is efficiency, right? Like, that's the reason we did that whole thing. That's the reason we studied recursion. That's the reason we did this divide and conquer and this merge. Insertion sort was a lot easier to implement. I'd rather just do insertion sort. Oh, that's just main method. This is the whole algorithm right here. Just doubly nested loop. Clearly n squared algorithm here with a doubly nested loop, each doing n amount of work. So the whole point of adding all this complexity and recursion and all this was to be faster. We want to get to an n log n sorting algorithm instead of an n squared sorting algorithm. But oh shit, my merge sort is 5 milliseconds and my insertion sort is 4 milliseconds. Insertion sort's faster. Why do we do all that work? And this is often going to be true when we're talking about asymptotic runtimes. The better asymptotic algorithm is usually going to be slower because there's so much more overhead, there's more stack frames, there's a lot more going on. I'm creating more lists. There's a lot of overhead in this. So it's going to be slower when n is small. Once n starts getting big, as n gets big enough, asymptotics will always take over. So once we start jacking n up and start having bigger lists to sort, let's try 10,000, asymptotics will always take over. Those constants, the constants are going to wash away, and the asymptotics, n squared is eventually, no matter what the constants are, will be slower than n log n. So we put this up to 10,000. Merge sort is at 41 milliseconds. Insertion sort, 482. Merge sort is already 10 times faster than insertion sort. And once we get up to values this big, what actually takes up a lot of time, well, let's go one more. Let's go to 100,000 first to really make that point. What ends up taking a lot of time, we got 1 second on merge sort here, and insertion sort is going to give me time to explain this. What actually takes up a lot of time, a pretty slow operation, is printing things to the screen. Any I/O that you have is going to take, input-output that you have, is going to take a long time, whether it's reading, writing to disks, reading, writing to the screen, talking to a database, talking to a network. It's all very slow. So printing to the screen is actually really hurting our runtime here, and we have insertion sort at half a minute versus 1 second, so 30 times faster. And if we run this again, let me not run insertion sort anymore, because insertion sorts, that n squared is just really not doing it. But 970 milliseconds for merge sort, 140 running again, just without printing to the screen. So printing to the screen was by far the slowest part of merge sort in that case. So we're down to 140 milliseconds, and let's go a million. Let's go right to 10 million. 10 million elements. Insertion sort would take forever here. We wouldn't have enough time in the rest of the semester to wait for insertion sort. Merge sort, no big deal. We start to feel the runtime a little bit, but 9 seconds, I'll live. Well, let's go one more. Should have time to do this. Let's go one more, and let's do Java sort. Let's use Java's built-in library. Java has teams of engineers working for decades to get the best sorting algorithm they can possibly get. So we expect it to be much more efficient than whatever I can do in a lecture, I hope. So let's see what they do. Sorter.sorting, collections.sort. And Java does it inline. You give it a reference, and it does go to the heap and messes with your list and changes it that way. So numbers, not sorted numbers. We're going to do our test to make sure that it is actually sorting. Let's get rid of the insertion sort test, because it'll take forever, and then run both tests side by side. We got about 9 seconds we expect with our merge sort. Let's see what teams of engineers with tons of time on their hands, let's see how much better they can do. Still 9 seconds for our merge sort that we whipped up in a lecture, and 6 seconds for Java's merge sort. Faster, but not incredibly so. As long as you're hitting the right asymptotic runtime, yes, we have some constants that are slowing us down, that we could work at it, we could really squeeze some more efficiency out of our algorithm, or use different algorithms like Java's not using merge sort. But we're just going to chip away at that constant. As long as we're in the right asymptotic range, that right asymptotic runtime, we're going to be doing pretty good. But if we're hitting n squared instead of n log n, this is 10 million on 100,000, insertion sort was still 6-7 times slower than this on 10 million. That's a huge difference. So hitting them asymptotics can really matter. Constants, yes, constants sometimes matter. If you can get this 25% increase in efficiency out of your code, you should go for it, depending on what application you're doing, what you're doing. My music. What happened to my music? The music should have cut me off.